Now, section 14.3, surface area. Surface area. Okay. Surface area is the total area of the faces and the curved surface of a solid figure, like this. Okay. Mathematical description of the surface area is considerably more as a sphere assigned surface area using their representation as a parametric surface. Okay, so for finding the area, surface area, can be formulated in this way. When G is a function of x and y, this surface area, which is the accumulation of the surface area on this domain on xy axis, can be written in this way: double integral of this function with respect to x and y on A. Okay, so when this G is a function of x and y. And similarly, the surface area of the function x of x, which is a function of y and g on the different domain A prime, can be found in this way. Seemingly, when function y is a function of g and x, then the surface area of this y on the domain in gx plane as a double prime can be formulated in this way. Okay, see the examples. 1. Find the surface area S of a part of circular cone G, like this, that lies between G is equal to R1 and G is equal to R2, when R1 is less than R2, like this. So this domain D can be written in this way, and X this, and G can be written. G is this, where partial derivative of G with respect to X is this, and partial derivative of G with respect to Y is this. So from the formula, the surface area can be formulated in this way: square root of 1 double integral of this on dA on the domain D, which is this. And here the function is square root of 1 plus round G over round X, round G over round Y, like this. So we can simplify this in this way, and this is constant, it can come out. So double integral of this one is just the area of this region, which can be easily find like this. So this is one answer for that. Okay. And then the next example, here this circular cone represent this. So we do integrate from here. When R1 is here, R2 is there. So we do integrate from here to here. Okay. Anyway, the next example shows find the surface area of the sphere. This one. We are looking for the surface area. How we can get it? Okay, here, so we try. So this is a function. We can write this as the G is a function of x and y. So we find the partial derivative of G with respect to x and partial derivative of G with respect to y, and then we can form the function like this, and then we figure out this sphere is from in this area. So if we think this in a polar coordinate, then the radius starts from 0 to A, and the angles are from 0 to pi over 2. So it's better use the polar coordinate to the double integrals. So after we simplify the function like this, square root of this, and then with those information, then we can easily substitute this in in polar coordinate. So this x square plus y square turned to r square, and dx dy turned to r dr d theta. And here r from 0 to a, and theta from 0 to pi over 2. So we have the integration like this, which is easy integral for the single variable, because this has nothing to do with theta, so we only find the integral of this one, then multiply the constant to have 4 pi times a square as the surface area of this sphere in first octant. Okay, now find the surface area of the portion of the sphere, x square plus y square plus z square a square, and that is inside the cylinder. X square plus y square is equal to ax. Like this. Okay, this is a new problem. Let's think. Okay, so we are looking for a surface area, part of surface area of this sphere on this domain. And so now we think g as a function of x and y. So we can utilize the formula for the surface area as we saw in the earlier page. Then we do use the polar coordinate to transform the formula. So we look for round g round r and round g round theta when r is r cosine theta, and y is x is r cosine theta and y is r sine theta. And then the formula was replaced with this one in the explanation just before this example. Now, by substituting this in here, we have this function. And we have this function now, with the r dr d theta, like this. And then, the legend, the integration legend, in the polar coordinate, in here, theta is from 0 to pi over 2. So theta from 0 to pi over 2. And r, this r is, we are looking for this region, the region here. The r moves from 0 to a cosine theta from the observation. So we have this integral, and this gives us this integrand, and then to integrate 1 minus sine theta from 0 to 2 pi, and then multiply 4a square to have this value. And this is one example which is related to the earlier example. And then the section 14.3 has the examples and the exercise problems in here. Then that has the solutions and problems with the code to do the simulations like this. We are looking for the surface areas in rectangular coordinate and polar coordinates. Okay, I think that's the end of this section. We will continue the section 14.4, and if you have any question, feel free to ask me now.